Welcome to Fast Math Solutions on Maths with EJD. In this video, our focus is on how to prove that the sum from one to any number is actually the same thing as the last number times the number after it divided by 2. In one of my previous videos, I showed you that if you want to add from one to any number, all you just need to do is pick the last number, multiply by the next number after it, and divide by 2, and you get your answer. So here is actually the proof for that. So let's go. You want to prove that 1 plus 2 plus 3 plus all that up to n is equal to that n multiplied by n plus 1 divided by 2, just like I explained to you. So of course this borders on mathematical induction, and in a previous video I also did on mathematical induction. I told you there are 4 steps in mathematical induction. The first step is to prove that it is true for n equals 1, that whatever you're proving is true for n equals 1, and then it is true for n equals 2. Of course, you can keep checking for other numbers, right? And then once it is proven that it is true for 1 and 2, then you can now assume that it is true for n equals k. And then you go to step 4, which is which is called the inductive state, or the inductive state, where you actually establish the proof. And that is where you say that you show that it is correct. It is verified. It is proven for n equals k plus 1. Now, the previous example we did was to show that a particular expression was divisible by 9. So, but in this case, we want to prove that this sum is equal to this formula. So, as you can see already, of course, the first step is to prove that it is true for n equals 1. Don't forget that the left-hand side, we take it as a sum. It is actually a sum, and the right-hand side is a formula. So, and that's how the treatment is going to go. So, now, before you even go too far, remember that at the end of the day, you're expected to get this expression. At the inductive stage, you want to end up showing that for that the inductive stage, of course, is where n equals k plus 1. So it means that at that stage, you want to be able to prove that this formula side will translate to this. For n, you have k plus 1. Then, of course, for this n again, you have another k plus 1. Of course, plus 1. So this is n into n plus 1 divided by 2. So at the end of the day, if your proof is going to be true, this is the final result you should get. And I'll explain to you how to get there. So don't forget, the end result is to show that this formula side is such that for every n, you have k plus 1, basically. So if you can show that, then you would have proven this this expression. Okay, so let's go. Again, the left-hand side is seen as a sum. The right-hand side is seen as a formula. So, and that is why if for n equals 1 now, n equals 1 implies that you pick the first number because you're summing things up. So it means you're just taking just the first number, just the first one. And for the right-hand side, you're slotting the value of n into that expression. So n equals n plus 1 will now be 1 into 1 plus 1, of course, divided by that 2. So you have 1 into 2 divided by 2. 2 cancels 2, and you have 1. So you see the right-hand side is 1, and the left-hand side is also 1. So it means it is true. That expression is true for n equals 1. So you go to the second stage, where the second step, where you prove that it is true for n equals 2. So for n equals 2, you take the first two, 1 plus 2, okay? Because this left-hand side is a sum, so that's what you have here. Left-hand side, 1 plus 2 equals 3. Right-hand side, you put 2 into the expression, so you have 2 into 2 plus 1 divided by 2. So you have that means 2, then 2 plus 1 is 3 divided by 2. 2 cancels 2, and what you have left is 3. So you see that for the sum side, which is the left-hand side, you get 3. For the formula side, you also get 3. So it means it is true for n equals 2. Now, if you're writing a theory exam, it's after each day you should write something like, so the expression is true for n equals 1. So the expression is true for n equals 2, and then the third step is to assume that it is true for n equals k, because there's really nothing you can do beyond assuming that it is true for n equals k. And to do that, wherever you have n, you change it to k. So instead of having 1 plus 2 plus 3 plus all that plus n equals n into n plus 1 over 2, you end up having 1 plus 2 plus 3 plus everything plus k equals k into k plus 1 over 2. So every n is replaced by k. And that's all you get to do at the third stage. So the final stage, which is called the inductive or the induction stage, the inductive stage, or yeah, the inductive stage, this is where you actually show that the formula is correct. And don't forget, just like I told you, based on the particular expression we have, at the end of the day, for you to show that it is actually correct, it means that instead of having n into n plus 1 over 2, you should have, for every n, you have k plus 1. So k, for n here, you have k plus 1 into this other n now will be k plus 1, then plus the 1 outside divided by 2. So if you can get this, then you can say that you have proven that it is correct. So, and that means it is true for all natural numbers. So step 4 is to establish it for n equals k plus 1. And see what you do here. When you did for k, you had 1 plus 2 plus 3 plus all that up to k, you know. But and then this was at the right hand side. So what you're going to do at this point is to replace for so you are taking it a step further. You're adding one more step, and of course that next step is k plus 1. And for you to, since this one is already equal to this, so to balance the equation, if you add k plus 1 to this side, you must add exactly the same k plus 1 to the right hand side. All right. So this was already equal to this. So whatever you're adding here, you need to balance it up on the other side by adding the same thing on the right hand side. And guess what? Once you're able to do that correctly, the next thing you need to do is to now solve the right hand side until you get to the goal of k plus 1, for that first n, into k plus 1 divided by 2, So once you add k plus 1 to both sides, once you add k plus 1 to both sides, then the next thing is to solve the right-hand side until you get what the expression we're expecting. So let's go. So here you have k into k plus 1 over 2 plus k plus 1 all over 1. So the LCM of 2 and 1 is 2. So 2 in 2 is 1. 1 times k into k plus 1 is k into k plus 1. Plus 1 in 2 is 2. 2 times k plus 1. You have that. So the next thing is you can see you don't even have to expand. K plus 1 is common to both sides. So you can factorize k plus 1 here. So and if you take k plus 1 out, what do you have left here? K here, and then 2 here. So you have k plus 1 into k plus 2. So all over 2, that's what you have there. But what are we expecting? You already know what you're expecting. You're expecting k plus 1 into k plus 1 plus 1. So, and the way to get that is you can see k plus 2 here. So instead of having k plus 2, you can just say, 2 is 1 plus 1. So you can say, of course, this k plus 1 is settled. This is what we need here. And then for inside now, k plus 2 is k plus 1 plus 1. And of course, to make it look like that, you can now put it together. So you have k plus 1 here. Then k plus 1 can actually be expressed as k plus 1 in brackets plus another one, this one divided by 2. And this is exactly what we're expecting. So you can then conclude that since the expression is true for n equals 1 to n equals 1 to, then of course k and k plus 1, then it is true for all natural numbers, like that. So with that, we've come to the end of that proof. So, and of course, it works because I've done it in the previous video. So thanks for listening. If you have not subscribed to this channel, please feel free to subscribe and press the notification bell so you can always get video alerts whenever a new video is uploaded. See you in the next video.